Hello everyone and welcome to the course of probability. Differently from what I've done in the course of linear algebra, where I spent quite a lot of time trying to motivate why linear algebra is useful, I don't think that I have to do the same for probability. In fact, it's enough to show up to 10 scientific fields in which probability plays a major role to show how important and diversified is the application of probability in modern-day science. This course is intended to be just an introduction to probability and is composed by just these two chapters here. For me, what's important to underline since the beginning is that I chose to be as close as practical applications as possible. Applications will not be used only as examples, but also as motivations in order to introduce the concepts that will be discussed in this course. Let's start our journey with Chapter 1. Let's start this gentle introduction to probability with a little bit of history. A legend says that the theory of probability was born in the 17th century when Chevalier de Marais, a writer with a passion for gambling, was losing a lot of money due to the wrong assumption about the chances of getting a double six in a roll of two dice, which is actually a problem that we will discuss during this course. Chevalier de Marais was lucky enough to have two great mathematicians as friends. I'm talking about Blaise Pascal and Pierre de Fermat, and he asked them to develop a mathematical formulation of gambling odds in order to improve his chances at winning. Incredibly enough, the work of Pascal and Fermat led to the development of probability. Probability wasn't considered a serious mathematical discipline until the advent of the great Russian mathematician Andrei Kolmogorov, who provided a rigorous formalization in the 20th century. The reason why it took so long to formalize probability is that Kolmogorov had to merge two different disciplines of mathematics that were developed between the end of the 19th century and the beginning of the 20th century. The first discipline is set theory, that was developed by the Russian-German mathematician Georg Cantor, and the second one is the theory of measure and integration, which was developed by the French mathematician Henri Lebesgue. You don't have to be worried about the appearance of these two mathematical disciplines. In fact, in this course, we will minimize the mathematical formalism in favor of concrete examples and practical applications. The mathematical definitions and results that we need in order to develop probability will be introduced incrementally, integrating them in worked example at each step. Learning a new mathematical discipline is like learning a new language, and in order to speak that language, we must learn its vocabulary. This is precisely what we're going to do in this section. Let's start with the concept of random experiment. An experiment that, reproduced in exactly the same way, may lead to different outcomes which cannot be known in advance, is called random. This is the opposite of what happens for a deterministic experiment, in which, once we set up the same initial conditions, we get the same outcome for every repetition of the experiment. Once we have a random experiment, we can talk about its sample space, also called probability space. This space is the set that we will indicate with the letter S in this course, that contains all possible outcomes of this random experiment. To better understand these definitions, let's consider two examples. The first random experiment that we consider is tossing a coin. Then its sample space will simply be this one, where H stands for head and T stands for tail of the coin. The second example is very cute. In fact, imagine that you have a puppy, a cat, a dog, whatever you want, and the random experiment consists in calling the puppy and measuring the reaction time t. In this case, the sample space, that is the set of all possible outcomes, will be the interval 0 plus infinite. Why that? Well, because we have to consider all instants of time between the two opposite situations in which your pet is very energetic and so reacts almost instantly. In this case, t goes to 0, or your pet is very lazy and so it never reacts. In this case, t goes to infinite. I chose these two examples because they show that the sample space can be either discrete or continuous, and finite or infinite. With the word discrete, I mean that we can label the outcomes belonging to the sample space with integer numbers. Let's consider these two examples here. In this case, we have that tossing a coin has as sample space head or tail. So we can associate, for example, 0 to head and 1 to tail. Instead, with the word continuous, I mean that we can label the outcomes belonging to the sample space with a real parameter. This is exactly what happens in this example here, where we measure the reaction time of a puppy. In this case, in fact, the instants of time belonging to 0 plus infinite are real numbers that we indicate with the symbol t. The meaning of finite and infinite changes if we consider a discrete or a continuous sample space. These two sample spaces here are both discrete because we can label their outcomes with integer numbers. However, this one is finite because it contains only two outcomes, and this one is infinite because it contains an infinite amount of outcomes. In the case of a continuous sample space, finite or infinite must be read as bounded or unbounded. In this case, we have that this sample space is infinite because it is unbounded, and this continuous sample space here, that is all the real numbers between 0 and 2, is finite because it is bounded. In the sequel, we will see that these distinctions between sample spaces are really important because they determine the way in which probabilities can be assigned. Now let's move on to the hugely important concept of event that we introduce through this example. In this example, the random experiment consists in rolling a die. The sample space is, of course, given by all these outcomes, that is, in mathematical terms, by the set of all natural numbers between 1 and 6, and so it is a discrete, finite sample space. One of the most natural questions that we can ask in this case is whether the outcome will be even or odd independently of the numerical value. The even outcomes will belong to the subset E of the sample space S, given by 2, 4, and 6, while the odd outcomes will belong to the subset O of S, given by 1, 3, and 5. This example gives a nice and clear motivation of why in probability it is convenient to introduce a name for a subset of S, that is, a collection of possible outcomes and not only one single outcome. In fact, this gives us the possibility to group together outcomes that share a common property, in this case of having value even, and in this case of having value odd. More generally, we give the following definition. An event is any collection of possible outcomes, that is, any subset of the sample space S of a random experiment, including S itself, which means that all the outcomes are considered, or the empty set, which means that no outcome is considered. We say that an event E occurs if the outcome of a random experiment belongs to E. In the previous example, if we roll the die and the outcome is 3, then the event O occurs because 3 belongs to the set of odd numbers. Instead, if we obtain 4 as outcome, then the event E occurs because, of course, 4 belongs to the subset of even numbers. Now, since events are subsets of the sample space S, it shouldn't be surprising the fact that what we call the event operations are nothing but the typical transformations that we can perform over the subsets of a given set. We have, of course, the union. The union of two events is the set that contains the elements of E and those of F without repetitions. For example, if we consider E given by the natural numbers between 1 and 4 and F the natural numbers between 3 and 6, we have that E union with F is the set of all natural numbers between 1 and 6 without repeating 3. Then we have the intersection. The intersection between two events is the set that contains only the elements shared by E and F. In the previous case, only 3 is a shared element between E and F, and so the intersection between E and F is given by the set whose only element is the number 3. The third event operation consists in taking the complementary. The complementary event is indicated with this symbol here and consists in considering only the elements of S which are not contained in the event E. Keep in mind that when we want to compute the complementary of an event, we must very well specify the sample space. Let's consider this example. The sample space S is given by all the natural numbers between 1 and 10, and the events E and F are the previous ones. Then the complementary of the event E is given by all the outcomes that belong to S and that don't belong to E, that is, the natural numbers between 5 and 10. Instead, the complementary of F is given by all the outcomes of S that don't belong to F, that is 1, 2, 4, and all the natural numbers from 7 to 10. We can give a probabilistic interpretation of the event operations. In fact, the union means that at least one event occurs. The intersection means that both events occur simultaneously, and the complementary means that the contrary of the event occurs. Let's consider the particular case in which the intersection between two events is empty. In this case, the probabilistic interpretations that we have just introduced says that the two events cannot occur simultaneously. The two events are said to be disjoint or mutually exclusive or incompatible. We can extend this definition to a set of events E1, E2, En by asking that the intersection between Ei and Ej is the empty set for all index I and j. In order to have a concrete example at hand, consider rolling a die. In this case, we have events E and O that represent the fact that we roll a die and we obtain an even or an odd outcome. In this case, it is clear that the events are disjoint. Event operations of union, intersection, and complementary are related together by the famous De Morgan law. The first De Morgan law says that if we take the complementary of the union between E and F, then this is equal to considering the intersection between the complementary of E and the complementary of F. The second De Morgan law says that if we take the complementary of the intersection between E and F, this is equal to considering the union of the complementary of E and the complementary of F. So, as you can see, the complementary reverses the role of union and intersection. We will also need in the following the so-called distributive relations between union and intersection, which are indicated here and here. There is a nice mnemonic rule that you can apply in order to recall the distributive relations. In fact, you just have to associate the intersection to the multiplication and the union to the sum, and then use the distributive rules that you know from algebra. Let me show you this mnemonic rule in this case. We have that E intersection with F union G can be thought as E times F plus G, and we write E times F plus E times G, but E times F can be associated with E intersection with F, E times G can be associated with E intersection with G, and plus can be associated with the union. The last definition that we give of the typical vocabulary of probability in this section is given by the concept of partition, and in order to motivate it, we consider again the act of rolling a die. We have seen that we can define two events, E and O, which contain respectively the even and odd outcomes of rolling a die. We have also seen that these events are disjoint, but we can also highlight another characteristic, that is, their union reconstructs the sample space. In fact, E union O gives rise to S. The events E and O that we have just discussed are nothing but particular instances of what is called a partition of a sample space. The formal definition is the following. Consider a collection of events EJ, which are disjoint and such that they reconstruct the sample space S through their union, like this. In this case, the events EJ are said to form a partition of the sample space S. To underline the fact that in a partition the union is performed over disjoint subsets of S, instead of using the usual symbol for the union, we replace it with this symbol here.
We have just seen that probability has its own very peculiar language. For you, in order to understand what follows, it is important to be fluent in this language. You should know without hesitation what's a random experiment, what is the sample space that can be built with random experiments, what are its partitions, what are events, what does it mean that an event occurs, what are the operations that can be performed of events, and what does it mean that two events are incompatible. To underline once more the importance of the probabilistic language, let me tell you that it is very unlikely that you can understand what follows if you don't master these concepts here. I strongly suggest to test each other regarding the degree of knowledge that you have acquired so far regarding these concepts.
In this section, we're going to introduce the very important concept of probability function. In order to introduce it, imagine that we perform an experiment n times in an identical way, and that some outcomes happen more often than others. If we indicate with this symbol here the amount of times that an event E occurs, then we can introduce its frequency of occurrence as the ratio between the number of times that the event E occurs and the total number of experiments performed. It turns out that for centuries, the probability associated to the event E was defined through this following limit. That is, the limit when n tends to plus infinity of the ratio between the frequency of occurrence of the event E and the number of experiments performed. This approach is of course very intuitive. However, it has some serious drawbacks, not only of theoretical nature. For instance, can we assure that the limit exists? If so, how can we practically compute it? How many experiments do we have to run in order to have a fair estimation of the frequency of occurrence of the event E? In 1933, the Russian mathematician Kolmogorov, that we have already mentioned, published the book Foundations of the Theory of Probability, in which he overcame the problems related to the frequency approach, those mentioned here, at the expense of a more abstract interpretation of probability. So his approach was less intuitive, but much more powerful. The concept that lies at the basis of Kolmogorov approach is the probability function. This one is a map that takes events as input and gives back values in the set 0 and 1 interpreted as probability as output. For example, 0 is attached to an impossible event, 1 is attached to a certain event, that is, an event that occurs with 100% probability, and 1.5 is attached to an event that has 50% probability to occur. The formal definition of probability function P is quite abstract, and as I told you, I want to avoid as much as possible introducing such definitions without first provide a motivational example. I think that the example of tossing a coin is well suited for this job. In many books of probability, you will read fair coin. This simply means that you are tossing a coin that a priori has the same chance of landing heads or tails. Now, regarding the probability function, we already know that the sample space for the tossing a coin is S equals to the set composed by heads and tails, and our intuition suggests that a reasonable probability function should assign equal probability to both heads and tails. Moreover, since S is equal to the union of heads and tails, we have that the probability of the union heads and tail is 1 because we have 100% certainty to obtain either heads or tails. Then we observe that since the complementary of the event heads is the event tails and vice versa, we have that the set on which the probability function is defined should contain also the complementary set of the event. Furthermore, we observe that the intersection between heads and tails and vice versa is the empty set, and since it's not possible to obtain both heads and tails simultaneously, a probability function should assign 0 to the empty set. Finally, if you recall the definition of partition of the sample space, we have that H and T form a partition of S. In fact, their union gives rise to S, and they are disjoint. Now, if you think about it for a second, the fact that the probability function must assign the same value to heads and tails, and the fact that the probability function of the disjoint union of heads and tails is 1, implies that the probability assigned to h and t is equal to 1/2, and also the fact that the probability of the disjoint union of heads and tails is the sum of probability of heads with the probability of tails. In spite of its simplicity, this example is very useful because we will see that in the next page, the definition of probability function is nothing but the mathematical generalization and abstraction of these 4 points. Given a sample space S related to a random experiment, we define a probability function like this. The domain of the probability function is a set that must contain all the events and their complementary sets, together with their unions and their intersections. In order to be called a probability function, P must satisfy the so-called Kolmogorov axioms. The first one says that when P is applied to the sample space, it must give back 1. The second axiom says that when we have a disjoint union, then the probability applied to this disjoint union of events is nothing but the sum of the probability of each single event. As I told you before, the requests on the domain of the probability function and on its behavior are nothing but the mathematical abstraction of the requests that we have highlighted in the previous example. Let's check the fact that this definition of probability function makes total sense by considering another very easy example, that is the rolling of a die. Before discussing the example, let me recall that an event is any set of outcomes. However, there is a special event called singleton, composed just by one outcome, which allows us to identify the event without ambiguity. In the case of rolling a die, the outcomes are represented by natural numbers between 1 and 6, and the singleton events that they identify are indicated with this symbol here. It is important to distinguish between an outcome n and a singleton event written like this, because the probability function is defined on events, which are sets of outcomes, and not on the outcomes themselves. Now, notice that the sample space is simply the union of all the singleton events taken separately. Moreover, recall that the die always shows just one face, hence the singleton events are always disjoint. The consequence is that we can write a partition of the sample space like this. Now, if no face of the die is different than the others, we can assume that the probability of each singleton event n is a constant value p between 0 and 1. We can now apply the second Kolmogorov axiom in order to write the probability related to the sample space as the sum of the single probabilities, as it is written here, but we have just said that all these probabilities are exactly the same and they are identified with p. So here we have 6 times p. Mixing the information that p of s is 1 and that p of s is 6 times p, we have that 6p is 1, that is, p is 1 over 6. This reasoning shows that we can obtain the intuitive result that the probability assigned to any face of a die is 1 over 6 using just the Kolmogorov axioms. Of course, the usefulness of the Kolmogorov approach reveals itself when we deal with more complicated problems. However, it is reassuring to check that it agrees with our intuition. In the next page, we are going to see that there is a general method to define a legitimate probability function without the need to check each time if the Kolmogorov axioms are satisfied. Consider a finite sample space S and a collection of n values pj, all belonging between 0 and 1, and such that they sum up to 1. Then the map written here is a probability function. P takes any event E and brings it to the sum of the numbers pk over the indices k such that the outcomes labeled with those indices belong to the event E. This definition here can seem quite complicated at first sight, but after examining the very nice example that follows, it will become clear. Here you see visualized a game of darts, and as usual, a player receives a score corresponding to the number assigned to each region in which the dart lands. The regions are these ones here. The entire dartboard is a circle of radius r, the regions are ring, and the distance between them is r divided by 5. The sample space of the game is the finite discrete set corresponding to 1 to 5, which are the scores corresponding to each region, and it is reasonable to assume that for a non-expert player, the probability of hitting a particular region is proportional to the area of that region. This assumption gives us a way to build the probabilities pk that appear in the previous theorem. Precisely, we define them as the probability of scoring k points given by the fraction between the area of the region K and the total area of the board. The only thing that remains to check if, summing up the values pk, we obtain 1. We're going to see that we can compute the area of region 1 and 5 directly. Let's start with region 1. By highlighting region 1, we immediately see that its area, A1, is given by the difference between the total area of the disk, that is pi r squared, and the area of the disk obtained starting from the center and arriving until the radius multiplied by 4 and divided by 5. The area of this disk is this one here. The area of region 5 is even simpler, because it is simply the area of the disk of radius r divided by 5, which is exactly the value that is written here. If we use the areas that we have just computed in order to calculate P1 and P5, we obtain these values that are written here. Without surprise, we have 36% probability of scoring 1 point and just 4% probability of scoring 5 points as a beginner. Now let's consider the intermediate regions. In this example, I have highlighted intermediate region 2. For intermediate regions, we can talk about their internal and external regions. Regarding region 2, we have that its internal region is this one highlighted in rose, and its external region is this one highlighted in blue. The area of the interior region of 2 is of course this one here, because we have to compute the area of the disk up to this radius here. The area of the external region 2 is given by the difference between the total area of the board, there it is, and the area of the board up to the radius r multiplied by 4 and divided by 5. There it is. Instead of writing 3, we can write 5 minus 2, and instead of writing 4, we can write 5 minus 2 plus 1. The usefulness of this manipulation is that we can use these formulas for any region K instead of just the region 2. Once we have the explicit formula for the interior and exterior of every intermediate region K, then we can compute the area of K simply by subtracting to the area of the whole disk the interior and the exterior area. We can understand why we consider this formula by fixing our attention on region 2. In fact, its area is what remains when we subtract to the area of the total disk the area of its external and internal regions. Now, if you go to the next page, you see the explicit expression of the area for the internal and external kth region. Then you can compute the area of the kth region, obtaining this value here. Now recall that the probability pk was defined as the ratio between the area of the region K and the total area of the board. Using the expression that we have just found and operating very easy algebraic manipulations, you can check that we arrive to this nice expression for the probability pk. Moreover, you can check that this formula gives the correct probability also for the case k equal to 1 and k equal to 5. So far, I kept talking about probabilities, but in order to check if these are indeed probabilities, we must verify the only condition expressed by the previous theorem, that is, the values pk must sum to 1. As a useful exercise, you can check that the sum of the values pk can be written like this, and it gives rise to 1. Thanks to the previous theorem, we can say that our initial guess was correct. That is, the fraction between the area hit by the dart and the total area of the board gives rise to a probability function. If you compute explicitly all the pKs, you find that the probability of hitting region 1 is 36%, region 2 28%, region 3 20%, region 4 12%, and region 5 4%. In other words, for a beginner, the probability of hitting decreases of 8% as we move from one region to the next internal one.